Stuck finding the root of an equation?
The bisection method is your detective.
The bisection method is a numerical technique used to find the root of a function within a specified interval.
Indeed, it relies on repeatedly halving the interval and narrowing down the region where the root lies. This idea can be extended into finding the roots of a function by finding that certain value c that would result in f of c equals to 0.
In bisection method algorithm 1, the following procedures must be taken to find the roots of a continuous function f of x. Initial guess. The initial value for a is 1 and the initial value for b is 45.
First and foremost, let us set up our table. Here we have 8 rows consisting of iteration a, f of a, b, f of b, c, f of c, and the decision. What is iteration? Iteration is the repeated application of a function or process in which the output of each step is used as the input for the next iteration.
To get the iteration for row 1, values are obtained by simple substitution. In the first iteration, we just put an output of 1.
In the bisection method, initial guesses are set with conditions. When evaluating f of a, you're essentially substituting the value a into the function f, denoted as f of a. So for instance, if the function is called group function of x, to find f of a, you substitute a into group functions of x, which yields group functions of a.
So, let's put it here. A is 1 and b is 45. This substitution automatically computes the corresponding value. Similarly, when evaluating f of b and f of c, you apply the same principle of substitution, utilizing the values in b and c. Let's use that formula c is equal to a plus b over 2, c is equal to 1 plus 45 over 2, where c is equal to 23. For function evaluation f of a, we have negative 4.59 something, f of b is equal to 19.45 something, and lastly, f of c is 3.82 something.
In determining the decision for the first row, a specific condition is established. If the value of f of c is equal to 0, the process stops.
However, if f of c is less than 0, the value of a is replaced with c. Conversely, if f of c is greater than 0, the value of b is replaced with c. This structure approach guides the iterative refinement process based on comparing the function evaluations at the midpoint, ensuring progression towards a solution.
Thus, in the first decision, we replace b with c because f of c, which is 3.82 something, is greater than 0.
Each row relies on the previous row's outcome. If it meets a stop condition, the process ends. Otherwise, the value for the current row is determined by adding 1 to the value from the preceding row. This ensured that the subsequence progresses incrementally unless a termination condition is met.
So in the second iteration, we add 1 to the preceding value and it is equal to 2.
Here, since b will be replaced with c, b becomes 23 while a remains 1.
As for the function evaluations f of a, f of b, and f of c, the process is the same with the first row.
The process is the same with the first row, where c is equal to a plus b over 2.
C is equal to 1 plus 23 divided by 2. C is equal to 12.
This row's decision is the same as the previous one. However, we added in the condition that if the value of c minus the value of the previous c is lesser than or equal to 0.0001, which can be accepted as root since it is approximately 0, then it will stop the algorithm. Lastly, in the following iterations, we'll just drag the values until the decision indicates the stop.
These are the iterations for a, b, and c, and their corresponding function evaluation, f of a, f of b, and f of c. We can see in this line graph the change of values of a, b, and c.
Furthermore, this pie chart indicates the count of decision. With 36.8%, replace b with c, 57.9% replace a with c, and 5.3% stop. Moreover, in this scatter plot, decision history is shown. Thank you.